Okay. And now desktop, share, and I guess we're now fine. Yeah.
So, as I mentioned, I'm Fionn. I'm today telling you something about computing organizations in a browser. And I will just start with a short recap of chemical organization theory, or at least the three words that are important to know for this talk. So given a reaction network N made up of molecules M and reactions R, we observe a subset of molecules S and want to define just these three words or these three concepts. A closure of a subset of S or of a subset S of molecules is if for all reactions in R for which the support of this reaction is in the subset we are observing, are also all in the product side of all reactions in this field. So if there's nothing new coming into from reactions of our set, and then we want to define the semi-organization because that's important for the algorithm a little bit later on. A semi-organization is a set of molecules that are consumed, for which are all consumed, are also produced within that set. So if our set is closed and all molecules are produced that are also consumed, then we call it semi-self-maintenance, and thus also a semi-organization. And lastly, if S produces all its molecules in a sufficient manner, then it is self-maintaining and thus called an organization. All self-maintaining and all organizations are also by definition semi-organizations, and this is a property we want to exploit later on. There's a mathematical term for checking if a set is a organization, and this is a set is self-maintaining if there exists a flux vector V so that the stoichiometric matrix of that subset multiplied with the flux vector is bigger than or equal to the null vector. So just to recap, a stoichiometric matrix is defined by all reactions that are in the closure and all the molecules that are in the closure. So a position Sij in a stoichiometric matrix corresponds to the net concentration or to the net count of the molecule I in reaction J. Yes. So then the question is, since we're all talking about semi-organizations, this workshop, how do we compute these? And currently, as of my finding, when I researched for my bachelor thesis, you had two options more or less. You could use org tools, which were proposed or which were presented by Zentler, Kaleta, Speroni, and Dittrich in 2008. Or you could use some self-developed tools or implementations of these algorithms, or have your own algorithms. These tools are not very easy to access if they're at all public. And org tools is more than 10 years old or more than 12 years old. It's not an intuitive process to get it running on newer machines. And that brought the question of how could that be, if there's an easier way to do that. So I thought, from my experience with programming, I thought to myself, what is easier than accessing a website? Virtually everyone can access a website today. So this would open the doors for creating web applications. And there are some benefits to a web application. So as I mentioned, accessing a website is fairly easy. You only have one code base that runs everything. And it's by standard multi-platform possibilities. So many people would think a web application is or will be slow or has long loading times, but with Google's advances, especially in its V8 JavaScript engine, it really is optimized and now is becoming a sort of good alternative to other programming languages. So that's where I will more or less start presenting my implementation of the computation. For my bachelor's thesis, I created a web application I call Weborg, which has a interface written in JavaScript or written in TypeScript and using the React.js framework, and having a cytoscape viewer to view all the networks and the lattice or the Huster diagrams, and has the constructive algorithm implemented in currently TypeScript, and solves LP problems using GLPK as WebAssembly, as a WebAssembly implementation. I will, on most parts, delve in a little bit deeper into that. So I will use a small sample or a small example network that I think most know. It's a 4-component network proposed by Dittrich and Speroni in their first paper in 2007. It's a really simple network, and you can see at least in REA file format how it looks. That brings me directly to the inputs and outputs of Weborg currently, and it can read or write directly in the application itself, REA and SBML. So REA is a homegrown, human-readable file format for reaction networks from Jena, and SBML is the systems biology markup language, which can also be used to present or to write down reaction networks or pathways or maybe other systems. SBML is a XML-based language that's not really readable if you don't know what all the special keywords mean. So I stuck to the REA format, and yeah, just will explain what the reaction is, what the reaction network is made of. So for the REA network, you need a number of components. These are just more or less counted, and a number of reactions. And we have 4 components or 4 species, A, B, C, and D, and they have 8 reactions that form the network. So we have a destruction of B and a destruction of C and a destruction of D. We have a reaction of 1A and 1B forming A and 2B, A and D, A and 2D, and so on. And these will then be read in and stored in a JavaScript object-like component, and then be processed further on. The same goes for SBML. You just drag and drop it on the editor, or you can just write it in the editor directly. And then it's just converted to a JavaScript object as well. The output is orgml lattice or an SVG. So orgml is a XML-based output format for organizations. So it will store the reactions in it, and it will store the species in it. However, it needs a SBML or a REA file with the orgml file to recreate the saved file, the saved organizations. But that's not a problem of Weborg itself, but a problem of the implementation before. That could be changed in the future. A lattice file .ltc is more or less the same, but it's for Huster diagrams, and it also needs a SBML or REA file to be fully recreated. The SVG output is a picture or an image. It's a scalable vector graphic. So no matter how large or how vast the reaction network or the Huster diagram that was generated with an SVG image, there's no compression or loss of information in details, regardless of size. So as I will go on and explain the other parts of the software, we will have this reaction system or this reaction network in mind, and to have a
So this is the input on the right hand.
That's the input, yes.
And your program, which is web-based, generates these types of output.
Yes. Yes. And so maybe I can share my screen from my laptop later on, because even though I mentioned nothing is easier than accessing a website, the website is currently not accessible because it's not hosted. But we have in mind to change that later. The landing page has this example loaded already in, but it's really just a text editor where you can read and write stuff. So if you...
So at the moment it's not online, it's offline.
Yes, but I have everything here to show it later if somebody wants to see it, or we can share my screen from my laptop on the Zoom.
We can do something right before maybe search install.
Yeah, but we can check that later. So to have a better overview of what we have written as a reaction network, we can display the reaction network and it will produce something like that. So we can see there are nodes for each of the species, and then we have also nodes that are not visible right here or right here for everyone on the Zoom call, that are reaction nodes. And from there on, we have connections for each input and output. So we have in this first reaction, as I mentioned, was 1A and 1B. So these two going to 1A and 2B. And these nodes are also movable, so you can click and drag and move them so you have a better visual placement. The software itself will try to place it in a circular manner, but some of the times it's not really a good overview. So there is also room for improvement in there. This is one of the cytoscape views in the software, so you can switch on all of the tabs around and have a look. And this can be exported to a SVG as well. So what I had in mind for some future development is that if you have this, so this is then a JavaScript object. And it would be nice to kind of convert these into the different file formats that you can use. So you can write a REA reaction network and maybe export it as SBML or something like that. Yeah. So if we are now satisfied with our reaction network, we want to calculate organizations or compute organizations. So currently I'm using the constructive algorithm as mentioned to find organizations. You can also find just connected organizations or reactive or erective organizations. And if you have found organizations, they will be listed in this list view. And you can also click on an organization to have more details about this. So in organization 3, we found we had 2 species, A and B, and these reactions make up the closure of this subset. When you click on Save Organizations, it will create an orgml file and then download that. So if we want to visualize these found organizations, we go to the Huster diagram viewer of the software, and there's a little algorithm that generates these Huster diagrams or lattices. So we first start by placing all the nodes in their hierarchical order. So each one of these levels is one hierarchical order of set. So there's all the sets with 1 species in it, all the sets with 2 species, with 3 and with 4. And then when they are all placed, we apply a trickle down algorithm. That's how I call it. I will start at the top and then draw edges to the layer below, which fits in this set. So if I fit A, B, C in there, D is left, so D is left over. So we would look in this if we have something that has A, B, C, or A or B or C, and A or B and C, and a D to fill that up. So everything is gone from here. But since we don't find one, we go a level deeper and search for something that would fit in there until all the species from this set are more or less gone. If they're all gone on that level, we won't continue to the next. But since in this case, there's nothing with a D, we go on there. Then going from this one, we do the same and so on. Yes. So after that's done, we create all the cytoscape graph elements. These are consisting of the nodes and the edges with their labels. And in this view, it's also possible to change the labeling of the graph. So I can say, okay, I just want to see novel species for the organizations, or I want to see all the species in an organization, or I just want to see the organization index. So if I just want to see the organization index, here would this organization would be called O2 or O1 and a 1. So indicating it's organization 1 and its size is 1. So this graph view can then be, or this lattice or Huster diagram can then be exported as an SVG as well, or it can be downloaded as a lattice file. So then I want to briefly go over the algorithm that is used. It's the constructed algorithm, the constructive algorithm, originally implemented by Center et al. And was similarly proposed by Dittrich and Spironi before. And it's, as I said, 2 steps. The first step is to calculate all semi-organizations and then check if each semi-organization is also self-maintaining. For calculating the semi-organizations, we start with the empty set and then generating the closure of this empty set and checking if that's self-maintained. When we save, then we save that into a list and start with the next level and checking from there. And that's going iteratively until we are on the top level. After we have done that, we have a list with all semi-organizations we have found and want to check. And then we're just, for each of them, creating a linear programming problem and giving it to the GLPK.js and checking it with a simplex algorithm. The great thing is we don't need to have the simplex algorithm run to its end. We just need to pre-solve it and see if it finds a solution. Because if it finds a solution, we know there is a flux vector that is desired, and that's all we have to do. We don't need to prove or to show what the flux vector is. Then that's more or less everything my software can do at the moment. Since we had some discussions about the software in the forerun, I would like to elaborate on some future work and thoughts, depending on each of the components. So for the text editor, I would like to have a validation process for files, because currently it just breaks. If there's a problem with the file, it doesn't say what the problem is, it just breaks and you have to reload the site. Also, it would be nice to have some sort of plugin system to have your own homegrown file format in it, because as long as it can convert to JSON, we can use it. And as I mentioned before, the export to other file formats. So because we're all converting to one inner object, more or less, we could easily convert it back to an arbitrary amount of other file formats. Also, my text editor is currently the Monaco editor. I don't know if any one of you have heard of that, but it's a not open source, but free to use text editor for JavaScript applications or for web applications, and currently bought or currently owned by a company that belongs to Microsoft. And I know that not everyone likes that, so I would like to have a step away from this editor and maybe have something else. Yeah, then I want to talk a little bit about WebAssembly. As I mentioned that GLPK is already in WebAssembly, written in WebAssembly. It is very fast. So as they state on their own website, WebAssembly aims to execute at native speed by taking advantage of common hardware capabilities available on a wide range of platforms. So in essence, you would write your code in something like C, C++, TypeScript, Python, Java, C#, something like that. And then with a special compiler, compile it down to binary code. Here in the example for C and C++, that's with mscripten. And this binary code can then be run in the web browser. So what my thinking would be is that when we can use this technology to rewrite the algorithms in C or C++, then compile them to be able to run in the browser, we could then use them to have more or less the speed of a native software solution in our platform running on everything. This also has the capabilities to have access to the shared worker threads, which is a simple way to have multi-threading in the web. That wasn't possible until four years ago or something like that. And I have also written a little test application that uses these shared worker threads. So even though they don't use the same memory, they have a shared array system or a shared array at the bottom, so they can fetch from the same data system. So you could split up work and just use it like normal multi-threading. I would also like to modularize and open it up for plugin use. So as I said, for more file systems, to have different algorithms in it. And maybe if somebody don't wants to use GLPK, they could also use LP-solve or something like that. That would all be possible. Then I would just like to summarize what I've talked about. I've presented Weborg as a tool to compute chemical organizations. It runs in a browser and is so widely available if it's online, and it displays lattices and networks for Huster diagrams and networks. And I would like to speed it up through WebAssembly and worker threads and expand it with modularization and plugins. That's it for me. Thank you.
We will have the round of questions for both together, so you can take the stage in the meantime. And while Simon gets ready, I would like to add that this is really cool to have a visual interface to work on these structures, because sometimes we can have lots of ideas about how they work, reactions and so on, but then when you really want to do it and it's in a command line, it's extremely hard to digest what the results are, and yeah, there are several problems. So it's we are really excited to start implementing the ideas we have been discussing, how to measure resilience, and we have some other algorithms that we didn't show, which do dynamical evolution in the sense of what was Stefan showing, like the curves and so on. We can obtain those things and do perturbation analysis, but that's going to be for probably next year's workshop. We will be able to show those results. So, okay, like go one slide.
Yeah, this okay. I cannot find the laser pointer now.
No, but the mouse is all right. Just move to your home.
So, why doesn't it work?
I think you can simply like click on the slides to just the mouse
can you help me?
It is a little funny.
Yeah, I see.
So not entirely responsive. So we need to go here, chat. So I create this too, and now yeah, you're. So you can use this. It's here.
So okay. First of all, thank you very much for having me here. And yeah, I will present you my bachelor thesis. So Peter Dittrich had the idea that the chemical organization theory could be applied to social communication, inspired by ideas of Niklas Luhmann. So the chemical organization theory deals with the identification of closed and self-maintaining sets of molecules in reaction networks, and links them to the behavior, to the dynamical behavior of systems. As the name already indicates, the chemical organization theory mainly deals with chemical systems and was designed for that, and mainly in the context of biology. However, reaction networks are suitable for the description of systems that involve the consumption, production, and transformation of entities of any kind. So you're not really stuck to apply it to chemistry, as we have already seen in the previous talk by others. So given the context of the workshop, I will not have another introduction to the chemical organization theory, but only have a brief introduction to the systems theory by Niklas Luhmann. Well, Niklas Luhmann developed a really elaborate theory on social systems that should serve as a general framework to describe each and every social interaction imaginable. So I will exclude everything that is not directly related to what we are using here. So first he did some observation on systems in general, and he identified operations as the basic elements in system. And operation can lead to following operations. So, and second, what for us is a system is some new emergent entity. So in order to have this entity, you both need like a cohesion, which is here the connection by the successorship relation between these operations. Like I said, that operations will lead to other operations. So in chemistry, for example, a reaction produces molecules that can be then used to have another reaction. And the second thing we need for a system is that it needs to differentiate itself from environment through operational closure. And it does so in a self-organizing process. So yeah, it's like closure in chemical organization theory. We have a set of operations that can only lead to operations like they are already in the set. And then there are some systems that are autopoietic, meaning that first they form themselves by a self-organizing process, and then they upkeep their existence and ensure that there are always enough operations running to ensure its existence and form. And next, within systems, differentiation into system and environment can be repeated, and this is leading to the fact that we can have subsystems. Okay. Then going to social systems, very brief. In social systems, we have communication as the operation running autopoiesis, and their social systems are in fact autopoietic systems. And in order to have successful communication, meaning communication that contributes to the autopoiesis of a system, we can only have that when the communicating agents follow two things, that they try to meet the expectations of the other agents, or when they try to predict the other agents' reaction to their actions. So to illustrate it really simple, you have to meet the expectations, otherwise you will be excluded from the discussion. Like yeah, maybe you will say something inappropriate and they will say, okay, I forgot I have something to do, and will go away, which means the discussion is over and the system has died. So in order to have a living social system, you have to ensure that the other ones accept what you are saying in a way and try not to stop the discussion. And yeah, so that's very simple put of it, but I think for mostly guys from chemistry and maths, it's enough to know about social systems. And again, to have a direct comparison, so in both the social systems theory and in the chemical organizations, we have some notion of closure. In social systems, we have autopoiesis, and in chemical organizations, we have self-maintenance. So some chemical organizations are autopoietic, but the problem is we are looking for a process, and we are calculating a process that might not be possible in the real world. So it's just a mathematical object. So one could speak of self-maintenance more in terms of like fighting the decay, which of course is self-induced. But yeah. And in both theories, we have some sort of hierarchical structure and hierarchical structure. In chemical organizations, we have the lattice, but basically it's exactly the same. And in social systems, we have rules for communicative connections based on expectations. And in chemical organizations, we have reaction rules based on molecule structure. So that made us believe that it should be possible to describe social systems with a finite set of rules. Okay, so with all these conceptual commonalities, we really think the chemical organization theory is really an empirical tool that can complement the theoretical work of sociologists that work with the social systems theory. Okay. So in my example is I examined scientific communication, and I did so because it's easier to measure the connections. So science uses mainly publications as messages for their communication. So we have a set of publications, someone reads them, gets an idea, thinks, puts work in, and outputs another publication. So there we have an increase of publications producing reactions. Then secondly, of course, for measuring autopoiesis, we only care about those publications that contribute to the autopoiesis, meaning producing more communications. So eventually most publications are not going to be cited anymore, not going to be read anymore, because they are just not interesting anymore, outdated, falsified, or whatever. So of course we need some molecular species. So I went for the domains of science and research fields in science. So these are just subsystems of the social system. And the network, the resulting network here, is a very specific one. It's a catalytic flow system that has some mathematical properties that will really help us with dealing with data. So the first thing, to those who know a bit about chemical organization theory, for catalytic flow systems, every semi-organization also is an organization. So we do not necessarily have to solve the LP problem to compute them. So that really helps us to deal with more data. Yeah, so now it was time to fill my model with data. And I got my data from the Web of Science core collection. So, oh, fuck my, yeah, there's a lot of reference data and metadata in general, but what is interesting for us is that they have lists of what the articles are citing. And also they have included a categorization into different research fields and domains that are based on the journals the papers are published in. So originally I planned on getting my data with an API, so I could have more, but the problem is that the API I would have needed is really expensive, so I had to go for manually downloading my data. I could not include that much, but I've downloaded an exemplary 12 research fields, and for each of them 25 publications with the highest citation counts. I did go for those with the highest citation counts because they are representing more communication, of course. And yeah, with them I downloaded more than 12,000 references. So this, yeah, sorry, just stuck. Okay. Here again, I have some really basic representation of how I derived the producing reactions. So given a publication A from the research field of virology that cites 3 different other papers, one from virology, one from both virology and cell biology, and then another one from chemistry. So maybe they would implement knowledge on viruses and how they infect cells, and utilize a method from chemistry to get some new knowledge about biology. And there we would end up with the reaction rule here, that 2 virology plus cell biology in this case led to 3 virology and 1 cell biology. You're shaking your head.
Yeah, I don't get it. I mean, because it's one there and 3 there. How do you come from?
Yeah, okay, I missed that. I had a selection of categories of only 12. So in this case, chemistry is outside my collection. Of course, if I would have gone for a full-scale picture, the actual reaction would have been 2 virology plus cell biology plus chemistry go to 3 virology plus cell biology plus chemistry.
How do you add them together? Why are they added together? Because they are. I mean, there is the one that is being cited and another the one that are cited. How do you add them together? What do you...
I was looking at what publications were used to produce new publications, basically. So,
So if one publication cites 3 publications
Yeah.
in your category, then you say those 3 have produced
yeah,
the one.
this is the support of the reaction rule that led to the production of the new publication. So, but
then you have only one publication, or then you see that there are
the others are not consumed, of course. You can still read them. You can still use them for other scientific work. Yes, exactly. And in this case, I have, because of my selection, excluded chemistry. Normally, you would have to include it as well, but yeah, I didn't have enough data for a full-scale picture, unfortunately. So I ended up with this network. So at this point, thank you, Fionn, for this nice picture. And I hope Awkweb is going online pretty soon. Yeah, it's hard really to conclude details from that. So here's just very short listed the categories I included for this particular network, where I have included 275 publications and their references from 11 different research fields. As we see, there are the categories are highly interconnected with one another. And one thing I worried about when thinking about making a full-scale picture of something like that, with like every category, which is in the Web of Science 250, and maybe include more publications per category, the reaction network would get too big to compute it. So I came up with a strategy that basically uses what I just recently learned about from Professor Heiligen about, is the degeneracy of a network. So basically you can exploit the mathematical structure of catalytic flow systems combined with my with the structure of my data to have a strategy that efficiently reduces the size of the reaction network. I will not go into the details about the math. If you want to know, I will explain later. But in this case, I was able to reduce 265 reactions to 99 reactions, and without alternating the organizational structure at all. So I got to this more easier reaction network with 99 reactions that promised to be computed much more faster. Actually, for a reaction network of this size, the difference is not that much, given that we don't have to solve the LP problem, and it's not that large already. So both can compute the organizations in like a second, but we were able to measure a difference in speed. So, and yeah, from that I computed the organizational structure. So here we can see a lattice of only the connected organization, because I thought when looking at it from a systems perspective, social systems perspective, it would be probably better to have only the connected organizations, so to have a coherent system really. And here, every of these ovals, this is an organization. And I think most interesting are the organizations really down here and up here. So why is that? It's just because here in the bottom, we can see like really basic dependencies on different categories of science. So for example, just because of the selection of my data, of course, sociology could potentially operate on its own. And the same would be true for mycology. But here, cell biology at least needs microbiology and vice versa to exist. So there you can identify really your neighbors, your important neighbors, and that should give like maybe also in an informed way to like maybe get distribute grants to interdisciplinary research, because automatically the system itself identified where to make interesting connections, and then we could like have these connections grow. The other important organizations are up here, because the very top organization is, of course, where the system is currently in. And from there, we could see next steps in terms of dynamical evolution. So maybe we could lose sociology and we would be perfectly fine, just given the selection, yeah, of course. And then the system of science could operate in that organization. And from there, maybe we could, if we lose here biodiversity and conservation, that would also mean that we would lose like 1, 2, 3, number 4, environmental sciences and ecology. So here we can also see how different research fields are indisposable for each other. Yeah. Okay, so let's go one step further. Of course, when making models based on data, we have to check if the data is actually representing enough to have a realistic model. So what I did here with the data I downloaded, I made various buildings of organizations where successively I started with 0 papers calculating the organizations, not actually, but then adding 1 paper, 2 papers, and see how the organizational structure changes. And what we should observe at the end is that if we add more data, the data is enough to represent it, the organizational structure should not change anymore. But in this case, unfortunately, it still changes. I think we are close to a point where it might not change anymore, but at this point, I cannot say for sure that I have enough publications per category. But one thing I also looked at was the number of reactions after the simplification. And this seems hardly to rise. So this is actually an indicator that we might get to a point where the data is sufficient. Yeah, and it's a bit related to what Thomas and we are now doing. So I added data, some of the data mutated the reaction network, and some of the reaction network mutations also led to a mutation in the chemical organization structure. So what I did is I tested the robustness of the organizational structure to in regards to changes of the reaction network.
Can I make a very quick comment?
Yeah, of course.
If we look at the curve, we see that the number of publications per category is a notion of how much do we allow to happen, like reactions.
Yeah.
It's a sort of diversity that we allow for the things to connect. And we see in the beginning a sort of increase in the number of organizations, and then we see a decrease. Why do we see a decrease? It is because there is
closure. Yeah.
There is closure. So the topics start creating organizations, but all of a sudden start connecting. So the number of organizations decrease because several of them will point to the same one, to the same big organization. So that is not a decrease. It's an increase in connectivity, what brings less organizations. But then again, you get recursively as you add more publications an increase because you have more ways to connect and so on. But then all of a sudden again you get a decrease. So these increases and decreases are a footprint of a process of diversity and then convergence and diversity and convergence. It's very interesting because we observe something similar, not exactly the same, but we have sort of kind of what's it called, like tomography, when you have like observations that you don't know really back what's going on, but we seem to have data that is coherent with that using random, semi-random networks.
Yeah.
So it will be interesting to see if knowledge is equivalent to knowledge creation is equivalent to a random process. Of course, we hope not, but
yeah. One thing came to my mind is that maybe here in this case I measured the amount of organizations as a very simple form, but the sheer number of organization itself doesn't really grasp the organizational structure. So you could have easily double the amount of your organizations without that much changes of in regards to complexity, I think. So maybe we could get to another notion for that.
Yeah,
and I think in the case of catalytic flow systems, this is a good approach to have like what are the numbers of reactions that still can change the network. Yeah. So in that case, we could not. Generally speaking, the problem is that we have to conclude from the data we have to data we don't have. Just like, okay, we observed a convergence, and with the assumption of our theory, we shouldn't have changes. But if we have a good measurement for robustness of organizational structure, we could maybe just say, okay, we have an organizational structure and it's really robust. So it doesn't matter if we add data, it doesn't matter what the data looks like, the organizational structure is now fixed. Maybe just a thought on this. Yeah, and then.
But it's actually not so different to the analysis that another member of the team who's not here is coming to Belgium next week. He did a similar analysis, but with the nuclear reaction networks. So at different temperatures,
okay,
you allow for different sort of like fundamental electron pair interactions, hydrogen electron, and creating. So these basic interactions that happen in the when a star is formed. So instead of having publications per category, you change the temperature of the environment, which allow the happening of a repertoire of 5,000 reactions, starting from like, I don't know, 300 and 500, depending on the temperature you change, and you can see a similar, and it's not that different, you know.
Yeah.
So this is it's a sort of diversity connectivity interplay.
Yes.
Yeah.
Did you shuffle the order of the publications and categories for this?
No, I just like they were in the list. Just
to see whether it's the same or if it changes. Maybe it depends strongly on the order of.
Yes. Could be possible. Like,
if not, it would be.
Maybe you would get to another curve, but still lot of variation. But yeah, I did not do that. Was only a bachelor thesis in the end. So yeah, and the last thing I did was still can't get forward here. As I didn't have the data to do a full-scale picture, I still wanted to have some thoughts on it, and wanted to make some thoughts if it's possible at all to have this full-scale picture with 254 different species. And so I did another row where in this case I added more and more categories, and I observed an exponential rise in the number of organizations. And if we would follow that, we would get to like 2.5 times 10 to the power of 48 organizations. I think in the end we would end up with much less, because we would have more interconnections, less closed sets, at least from the compared to the number of subsets at all. So, but it shows that it might not be possible to really have this full-scale picture, and then we have to find maybe some coarse graining, like maybe analyzing the basic sets, and then sticking them to single categories, then starting from there again. So maybe something like this. Okay. Yeah. Now go to the very first. Really not good with that. So yeah. As conclusion, I have to admit that the model I generated probably most certainly is not representative of the reality, and most of the causes in the end go back to lack of data. And something I didn't yet took into consideration is that, of course, we have high similarity to chemistry, but in the end, you have to pay respect to the fact that we don't actually have molecules, but subsystems, and then they can evolve. So the reaction network would change over time. So yeah, I didn't do that yet. But I showed that the chemical organization theory can be applied to the to social systems theory, and it's a very nice empirical tool because we can handle so much data, and we can reveal interdependencies that are not to be found with conventional network analysis. So Thomas is often holding talks on this, and yeah, we have these conceptual commonalities with social systems theory that just cry for the application of chemical organization theory to this. So as future work, the most important thing, of course, is that we have to gather more data to first allow a full-scale picture, then more publications per categories to be sure that we really have a representing set of data, and then we would have to divide the publications somehow into periods of time, so we can track the organizational structure and how it changes over time. Yeah, and I think this really is possible because after I did my bachelor thesis, there were changes in the Web of Sciences, and before the API that I would have needed it's really expensive, but now with the changes, I think that with a combination of two APIs, we might be able to automate the downloading of the most of all the references, at least. So we could save time there and have really fast data. And something that may be interesting is about the role of basic sets and synergy, especially, and what might their implications for social systems be. So, okay, thank you very much for your attention. Sorry for the slides. They really look different on my computer before I sent them.
Okay, so thank you. And we have very little time for questions because the next talks after lunch are set up for people who are not here. So we need to be kind of like really much sharper in time than as usual. But please, we have maybe 10 minutes for this. If anybody has questions.
I have one, but it's not, it's a big question. So just take the
Drop it
question.
and then we discuss
Yeah.
the lunch.
The question is for you, but it's actually for your group. I would like to hear more about your epistemology, which means what here the motivation beyond the fact of applying a formalism, which is the current family, to systems that are so different in nature. So you can apply it to the region of life, to cells, to a computational space, to the dynamics of publications. So these are systems, if you want to call that, which seems to be completely different. It might be the case, and you mentioned that at the end, so it's not really chemical reaction. It might share some common features. This one. So the question is the objective of your project just exploring the boundaries of application of a given format that you like for some reason? Or the idea is that this system in the end are the same kind of system? Or the danger is, are you excluding?
Yeah,
It's not,
well,
that's why it's not a question,
well,
it's a sort of debate. But
well, of course, there are, of course, there are various differences, but it's not solely about where can we apply this. And for me, it's for example, one thing Luhmann proposes is that we have rising and rising levels of system differentiation. And so we could use that to actually measure and quantify that. So might be interesting to have tools like this. So yeah.
Okay, maybe also a short answer. So my personal interest is in structural science. Structural science is the idea that you find the same structures on different domains. You understand the world, you can then separate this, understand the structures, and by that you understand then the world better because you find the same structures on different levels.
Yeah.
That's what, and my interest is, my personal interest is in structures that generate novelty. So it's structures that can create new things and that evolve. But and that have information. So that is just my personal motivation.
Yes.
But of course, now having these tools now, you can also go into the different domains and discover really interesting things, even if you are a bit, you don't know the details of that domain. Because in that domain, these tools are not applied. Because it takes ages, or not even decades, when you speak about neural networks, how long it took until they are applied in the domains. It took centuries or decades before they are applied. So we have just to do it by ourselves, even being let's say amateurs in that domain. So we are also interested in the domain to see now the social autopoietic structures in the communication of science now, in this case.
Yes,
Yeah, and
like this really.
Also, what you said is, so the third interest is how does our methods perform? So to get feedback on the property of the method, which you don't get when you have, let's say, just artificial data. So there are really these three aspects, I think, in doing this kind of strange thing, which is not in the normal way science is going. Usually you study 2 or 3 years papers and then you make a new one.
Two things are in this very case we have a practical application. So like managing science, like deciding who gets a grant or who does not. So you can have influence on the results you find there. What combinations of might be promising and which might not. Of course, you still have to look at the research itself as well, but it might help to have like establish organizations which specialize in funding this or that sort of interdisciplinary work. And most important, it's an example. So we are not sociologists, so we just try to come up with an example to motivate sociologists to think about implementing these, and they know better what really is interesting and what should be analyzed. So we just wanted to show it's possible to apply this, how it works, and maybe they have even better ideas than we have for researching things and what to research.
We continue the discussion in the lunch, and I encourage you to not take any detour, but go straight to the table, okay? Because we have speakers coming from abroad later, and they also have tight schedules that we need to match. Otherwise, they will not be able to speak at the workshop. So they have things to do as well, yeah. So, okay, we will be back for the online audience in 1 hour-ish, okay? 1 hour.
Great. Thank you, Thomas.
Likely
thank you.
Starting at 2:45.
Okay, thank you.
Yeah, okay. Any question?
No, thank
Okay.
you.
Yeah.
Thank you. Thank you.
2:45, 2:40. Okay. I'll try to bring them as soon as possible. Yeah, bye-bye.